This is lecture 7. So, in the previous lecture, we were discussing about some of the characteristics of a two-port network, right? Some of the characteristics of the two-port network that are necessary in order to realize our amplifier. We are halfway through, and we essentially stopped where we took a generalized nonlinear two-port network and we were trying to linearize it, right? So what did we do? A quick recap was the fact that we took a two-port network, a generalized nonlinear two-port, and if we call these ports, this port voltage is V1, and we call this V2, and the current, we call this as I1, we call this as I2. This is a non-linear two-port. This is RL, this is RS, and let's say you have a VI here. And we said that we understand that we require an additional power source, and we assume that the power source is inside the two-port network, right? And the power source that was inside the two-port network, it can be one power source, it can be multiple power sources, was instrumental in setting up the quiescent voltages, right? So they were instrumental in setting up the quiescent voltages across the two ports. And then we said that what happens if we perturb the port voltages, right? So where we stopped in the last class or in the last lecture was the fact that we said that let's say we have this generalized nonlinear two-port, right? And they have across its two ports, they have voltages of V1 and V2, and the currents going into the ports are I1 and I2. What happens if I perturb the voltages? What happens if I perturb? So we initially said that I1 is a function, some nonlinear function of the port voltages V1 and V2. And similarly, I2 are nonlinear functions of these port voltages V1 and V2. Note that the functions f1 and f2 need not be identical, right? And then we said that what if we perturb the voltages V1 and V2? So if I perturb the voltages V1 and V2, this becomes V1 plus delta V1, and this becomes V2 plus delta V2, and my current at the input will become I1 plus delta I1. Similarly, the output voltages, output currents at the port 2 on perturbation of the voltages of V1 and V2 will also be, can also be represented like this. And then we also said that this, as long as the perturbation port voltages delta V1 and delta V2, right? As long as the perturbation port voltages delta V1 and delta V2 are small enough, right? Are small enough such that the higher order terms of the nonlinearity can be neglected, then we can approximate this as the quiescent term, or that is the term from which everything started, right? The normal current, the quiescent current, that is f1 of v1 plus v2 plus del v1 del f1 del v1 around the quiescent point v1q v2q, right, plus del v2 del f1 del v2 around v1q Similarly, the current in the total current in the second port can also be represented as F2 of V1 comma V2 plus del V1 del F2 plus del V2 around quiescent port voltages, right? And then naturally what followed was the fact that this were identical, these were identical, and what we simply could write was del I1 was del F1 del V1. I am not writing the fact that not repeating the fact that these are around some quiescent points, that is implied. Similarly, del I2 became del F2 del V1 plus del F2 del V2, right? And naturally we saw that, and going from the we could realize that this is nothing but a set of two linear equations, right? And the incremental currents, right? The incremental currents were related to the incremental port voltages in a linearized fashion, right? So now we are in the domain of linear equations, linear circuit theory, which means that we can leverage all the good things, all the mathematical niceties of set of linear equations to enhance our understanding on the topic, right? And then we also continued on another piece of jargon, and the jargon was the fact that these del f del y's, right? So these del f del y's were nothing but incremental y parameters, right? Why y parameters or admittance parameters? It is admittance parameters simply because I am trying to develop a relationship of how current is changing when the voltage is getting perturbed. So essentially the coefficient of the voltage is admittance, right? And that's hence these parameters are called incremental y parameters. And why incremental? It's because it relates the incremental port voltage change to the incremental port current changes, right? Note that these are not absolute y parameters, these are not total y parameters, these are incremental y parameters, okay? And then we said that we could simply represent those currents and voltages as I1 is equal to y11 V1 plus y12 V2, and I2 became y21 V1 plus y22 V2, right? And what are the contexts of this y11 and y22? So the context was, now if I have the same two-port network, right? If I have the same two-port network and I want to relate only the incremental port voltages with the incremental currents, port currents, how can I relate them with? We can relate these incremental voltages and incremental currents through this set of equations, which are governed by, they are linear equations, but they are governed by the y parameters, right? And hence, I mean, we can rewrite these equations in a matrix form, and if I rewrite these equations in the matrix form, this is what we get. Right? So it is customary often to express this two-port network with its y parameters in the matrix form. Okay. So now let's take a step back. And see where we are right now and where from did we start. We started with the understanding that we require a nonlinear two-port, right? And we require at least a nonlinear two-port network in order to get an amplifier which can amplify power, right? So once we understood that, we figured that we need a framework to realize, or we need a framework to understand, analyze a two-port network which is nonlinear, because a generalized nonlinear solution doesn't exist. Then we played a trick, and what trick did we play? We played a trick that saying that we understand and we appreciate that a generalized nonlinear solution for any sort of nonlinearity is not possible. However, if we don't seek a generalized nonlinear solution, instead if we seek what happens if I change the voltages and the currents of a nonlinear system by a small amount, right? What is small can be related later on, but if we change the currents and the voltages in a nonlinear network by a small amount, then we saw that we can relate the changes between voltages and the currents in the nonlinear network with a linear relationship, right? So we got away with basically we cheated the system, and we said that, hey, I understand we have a nonlinear network. I'm not good at doing nonlinear mathematics, but I know how to do linear algebra. So I will twist the given system in such a way that I will bring it to my circle of competence. And what is my circle of competence? I'll make everything linear. And how did we make everything linear? We said that we will perturb the system by a small amount. We perturb the system by a small amount, and as long as the perturbation is small, then the relationship between the currents and the voltages remain linear. And in case of a two-port network, I have two voltage variables and two current variables, right? So which means that I should be able to relate them with a set of linear equations, and that's what we have done, right? Note that this is not yet, job is only half done, because we have only set up a framework to analyze a nonlinear two-port network, but we haven't yet come to that place where we have figured out what will be the input output characteristics when we apply a voltage source, right? So that is something that we will be doing next. So what am I hinting at? I am hinting at the fact that ultimately what are we looking for? We are looking for the fact that I have a voltage source Vi. It has a resistance associated with it, that is Rs. I have stuck it between this nonlinear two-port network, right? So this is F1 V1 V2, this is F2 V1 V2, right? So I have stuck this between a nonlinear two-port network, and with the understanding that there are currents and voltage sources, maybe inside, maybe outside, maybe somewhere, right? But we are not interested in finding out At present, we are not interested in finding out what is the relationship between the total V1 and total V2. At present, we are interested in finding out what happens if this input Vi, right, changes by a small amount, right? What happens if this input Vi changes by a small amount? What happens to the voltage across the RL? In other words, what we are saying is that we understand that if I apply a small perturbation Vi, the port voltage V1 will change. It will change to plus some small V1. The port voltage on the other port, port 2 will change. It will change to some small voltage, delta, some small voltage which is small V2. Similarly, the currents will also change from I1 to I1 plus small I1, I2 to I2 plus small I2, right? What are we interested in? Now we are interested in in finding the relation small v2 or small I2, right, and vi, right? Ultimately, this is what we are interested in, because that is what the perturbations are. And now the fact that we have developed a framework to relate perturbations of the ports, we can switch from this full-blown nonlinear network to our incremental nonlinear network and solve our set of linear equations, right? And that's what we will do next. Okay, so let's do it. So what should we do? We replace this nonlinear two port with their incremental equivalent. Okay, and we rewrite our equations. What are our equations? Our equations are I1 is equal to y11 v1 plus y12 v2. Okay, now note that I am not interested to get v2 or I2 in terms of v1, right? I am interested to get v2 and I2 in terms of vi. So I have to replace, I have to somehow juggle this equation to figure out what to do, right? So I recognize the fact that I1 is equal to Vi minus V1 over Rs, right? Or I can, instead of going in the division route, I recognize the fact that this is equal to Vi times Gs minus V1 times Gs, where Gs is equal to 1 over Rs. Similarly, you will see that we will require GL, which is equal to 1 over RL. So I just wrote it down up front. So what I'll do, I'll replace I1 with this. So this becomes Vi times Gs is equal to Y11 plus Gs times V1 plus Y12 2. Okay. Similarly, what is I2? I2 is Y21 V1 plus y22 V2. Okay. Now note that I2 is equal to, also I can write I2 is equal to minus V2 over RL, right? So this is V2. By the way, the notations of the two port networks are, I am pulling current into the port, right? So this becomes minus V2 over RL or minus V2 times GL. So I will replace this I2 with minus V2 times GL. So this becomes minus V2 times GL, or in other words, this becomes 0 is equal to y21 times V1 plus y22 plus GL times V2. Okay. So now have a look at these two equations. This one and this one. So what do you notice? You see, these are two sets of equations which can be written in a matrix form, right? So why am I interested in writing in a matrix form? Because it's a 2 by 2 matrix, it's easy to solve, right? So let me just write it in that format. So this becomes Vi times Gs 0 equal to V1, right? So now once you have it in this format, it's easy to find out what V2 will be. Now we know that V2 is equal to V naught, right? So in other words, V2 is nothing but, if I use Kramer's rule, this becomes right. So if I expand these determinants, what do I get in the denominator? I get y11 plus gs times y22 plus gl minus y12 to 1. And what do I get in the numerator? Get minus y21 pi times gs, right? So in other words, this is equal to V naught, right? This is V naught. In other words, what is V naught over Vi? Then denominator we get y11 plus gs times y22 plus gl minus y12 to 1, and in the numerator we get minus y21 times gs. Okay, right? So now what is our goal? Our goal is to maximize V naught over Vi, right? I want amplification, right? If I can, for a given Vi, right, if I can maximize V naught, And note that V naught is also across a resistor RL. So if I can maximize V naught, I can maximize the power delivered to the RL. So I can achieve that, right? So how can I achieve that? Mathematically it seems like if I simply set the denominator to 0, assuming that all the incremental y parameters are all positive, right? By the way, a note of caution, it's not necessary that the incremental y parameters should always be positive, because at the end of the day they are derivatives of a nonlinear function. It's not necessary that the derivative of a nonlinear function will always be positive. But as it turns out, in most of the regular devices that we use, they are positive, and so we will limit ourselves in this discussion to those conditions where all these y parameters are positive, right? So what do you think? How can I maximize this? I mean, the curious among you will obviously point to the fact that, hey, I can choose y12 and y21 and y11 and y22 in such a way that the denominator goes to 0, then I get v naught over vi to a minus infinity, right? Great. I mean, I'm looking for infinite, I'm looking for a high amplification. What's better than infinite amplification, right? Well, you might be right, but there is a problem, and let me try to convince you why the problem is a problem. Why is it actually a problem? So in order to appreciate that, let's express these y parameters in a circuit form, right? So one overwhelming theme that we will see in this course is we will try to express everything in the form of a circuit, because ultimately it's a circuit theory course. Not because only it is a circuit theory course, but in order to develop an intuition, of figuring out what these equations actually mean, because ultimately all these equations are pointing to some sorts of currents and some sorts of voltages. So we should be able to look at a circuit and then take a call of what happens to these currents and voltages if I express these equations in the form of a circuit, right? So how can I express these y parameters in a circuit form? Again, note that, let me write it down. So y1 is y11 v1 plus y12 v2. So what is this telling us? This is telling us that there are two ports, right? Let's say this port is, I call this v1. This is this port, I call this v2. What is this telling us? This is telling us these currents, at least this equation is telling us this current I1 is related to port V1, right? Current I1 is directly proportional to the port voltage V1, right? So what do you call an element whose current is proportional to its voltage? It's a resistance, right? In this case it's a conductance. So I can denote this as a conductance of value y11 or a resistance of value 1 by y11, right? So this is as far as this term is concerned. What about the next term? What about y1 to v2? What is this telling us? This is telling us that the current I1 is related to the port V2, the port voltage V2, with a proportionally constant y12. Now note that the relationship is between current in one port and voltage in some other port, right? So this is not a resistance per se, right? It's the change of current is not happening because the voltage across its terminals have changed, The change of current is happening because voltage in some other part of the circuit has changed, some other terminal has changed, right? So what type of controls, what type of sources do you think, or what type of element do you think will represent such a behavior? It's a voltage controlled current source, right? It's a transconductance. So what is the voltage controlled current source telling us here? So this essentially will be a voltage controlled current source whose control terminals will be somewhere else, that is V2, and the current through it will be Y12 times V2. What will be the direction of the current? What will be the direction of the voltage current, going up or going down? This will be going down, because ultimately I1 is the current through this plus the current through this, right? Okay. Similarly, what is I2? I2 is Y21 V1 plus Y22 V2. So exactly like, mathematically this is exactly like the port 1, just that whatever we have done in port 1 we'll have to do in port 2. So let me make space for it. So this is V2. So you will have 1 over Y22 here, and you will have a port, or rather you will have a current source, control current source, which is dependent on the voltage of port 1. So this becomes Y21. So this becomes your incremental Y parameter. Okay. Or rather this is I2. Okay. And now when you applied the incremental voltage source, what did we do? So we've simply applied Vi between its ports through a resistance Rs, right? And we stuck this resistance RL across. Okay. So now what is this equation here? What is this equation here telling us? What happens if y12 becomes equal, what happens if the denominator becomes 0? So when denominator becomes 0, you get infinite gain, right? What does infinite gain mean in real sense? Infinite gain in real sense means the fact that even without any input, you can get some finite output, right? When you have finite gain, a very large gain, in order to get an output, you still require an input. A small input can lead to a large output, right? So that's what a large gain means. Now, if the gain is infinite, what does it mean? You don't even have to give an input, you will get an output. Okay. So what does such a system, I mean, do you require such a system? We obviously don't require such a system. At least we don't need such a system to be an amplifier, because one of the requirements of an amplifier is to amplify if something is presented to it at its input. It should not start singing on its own, right? So this is not a good characteristics, that even without an input you get an output, right? So we'll have to steer clear of any such cases where we will get infinite gain, right? So infinite gain implies borderline instability, right? So often you will hear that infinite gain leads to oscillation, which is at times true, but essentially what one would like to convey is the fact that when you have infinite gain, you can get a finite output even without given an input, and that is not a characteristic of an amplifier. Whatever it is, it's not an amplifier. Since our goal is to get an amplifier, we'll have to steer clear of infinite gain. So when you say we have to steer clear of infinite gain, then one might say that I will choose these values of y1 and y22 in such a way that the denominator is not actually 0 but very close to 0, right? But there is a problem with that. And what is the problem? The problem is you would expect your amplifier to work under all conditions, right? You make an amplifier, you are selling it to your customer, and you don't know what type of GS and what type of GL your customer is going to apply, right? You don't know also whether these incremental y parameters will stay constant or it will change with temperature, right? Because ultimately everything is made out of real devices, and the characteristics of the devices might change if you take it to a very cold glacier or you can take it to a very hot desert, right? So you don't know whether these y parameters will remain constant across different humidity conditions, different temperature conditions, and so on. And also you don't know what type of GS and GL the user might be interested in plugging in, right? So given that you don't know all these things, you wouldn't want to take such a risk. Ultimately you are selling a product in the market, you would want it to behave in a proper way regardless of whatever you regardless of whatever conditions it is being used at, right? So what do you do? What is the obvious thing to do? So to prevent instability, so to prevent infinite gain, ensure y12 times y21 tends to 0. Okay. So, okay, one might say that why should we tend y12 times y21 to be 0? Why not the other terms, right? So, as you might have already guessed, the other terms have these GS and GL associated with them, which might not totally be in your control, right? So that is one aspect, and the other aspect is the fact that if you stare at this circuit, what do you think is the desired signal flow direction, right? What am I getting at is your signal is applied at port, essentially you are applying a signal at port 1, right? You are applying a signal at port 1 and you are getting the output at port 2, right? So essentially you are trying to transfer your signal from port 1 to port 2, correct? And through which part of the system do you think this transference of signal is happening? Note that this transference is happening through this critical element y21, right? Your signal, when you are applying a VI, it is generating some voltage across the port V1, and your port 2 is getting excited because the control current source at port 2 is sensing that voltage V1 and creating a current which it is using to excite the output resistance, right? So Y21 is the core of the amplifier, right? Y21 is causing the transference of signal from port 1 to port 2. What is Y12 doing? Y12 is sensing some of the output voltage and transferring it back to port 1, right? So this is Y21's job and this is Y12's job, right? And in an amplifier, given that you want signal transference from input to output, which one do you think is more important? Obviously Y21 will be more important. You would want Y21 to be as high as possible, because that's what is causing the transference of the signal. And what is Y12 doing? It is stealing some of the signal from output and bringing it to the input, and in that process also might lead, which might also lead to instability, right? So essentially what you want, you don't want this back transmission, this reverse propagation of signal from output to input through the network, which can cause potential instability. So essentially you would want Y12 to be 0, right? So we want Y12 to be 0 to prevent instability, right? Okay, what about the rest? So let's go to the next page and redraw this circuit again. So if Y12 is 0, I don't have anything there. So let me not sketch it. So if this is Y21 V1, this is Y22, and you have a load resistance, right? S over Y22. And this is V1. And again, what is our V0 over Vi? V0 over Vi is minus Y21 GS divided by Y11 plus GS times Y22 plus GL. And given that Y12 is 0, I can neglect this term. So what is the wish list now? What do I need Y21 to be? We would want Y21 to be, Y21 you would want Y21 to be as high as possible, right? Correct? So that's fine. So what about Y11 and Y22? What do you want them to be? If we stare at the equation, what is the goal? The goal is to maximize V0 over Vi. So which means I have to minimize denominator, which means we would want Y11 should tend to 0, and also Y22 should tend to 0. Correct? And if that happens, what is V0 over Vi? Then V0 over Vi becomes minus Y21 times GS by GS times GL. This means V0 over Vi becomes minus Y21 times RL. Right? So this turns out mathematically, but we have to also understand whether this makes any physical sense, right? So let's stare at the output port for some time being. So this is my V0, right? So how is the voltage V0 getting generated? The voltage V0 is getting generated when this current Y21 times V1, right? When this current is flowing into RL. Now note that this Y21 times V1 is flowing into a parallel combination of 1 over Y22 and RL. In other words, this current is getting divided between two resistors. Since the current is getting divided between two resistors, obviously the voltage V0 is not getting maximized, right? The voltage V0 is not getting maximized because RL is not getting the entire current, right? Ideally I would want Y21 times V1 to flow completely into RL in order to get the maximum possible output voltage. But in the presence of 1 over Y22, right, part of this current Y21 times V1 is getting into 1 over Y22, which is preventing all the current to flow into RL. So what is the wish list? What is the obvious thing to do? Obvious thing to say is that, hey, can we make 1 over Y22 to be infinity, or rather 1 over Y22 to be 0, right? I'm sorry, if we can make this 1 over Y22 to be infinity, then obviously all the current will flow into RL, which means that we would want Y22 to tend to 0. So what is the physical significance of Y22 tending to 0? The physical significance of this is no current division at the output port, right? Okay, so what about Y11 tend to 0? What does it signify? Now note that this main current Y21 times V1, this is the main current. Y21 times V1 is dependent on obviously V1, right? And if I have to maximize this current, what should I do? What should I ensure? I should ensure that V1 is maximized, right? Now what is V1? Note that V1 is the voltage across the input port 1 over Y11. And when can V1 be maximized? And why, under what condition can V1 be maximized? The condition under which the V1 can be maximized is when 1 over Y11 is infinity, right? Because ultimately, if you have a finite resistance at the input port, there will be a finite current, and moment you have a finite current, you will have a finite drop across RS, right? And moment you have a finite drop across RS, V1 will not be equal to Vi, right? Ultimately, if the maximum value of V1 is Vi, that can only be possible if there is no input current. Or in other words, you have infinite input impedance, right? In other words, if you have this impedance to be infinity, right? If this impedance is infinity, if there is no loading, if your network, if your two-port network doesn't incrementally load your input, then there will be no voltage drop across, no voltage drop of the input when you measure it across V1, right? So again, so this means this Y11 should tend to 0 to prevent or to maximize V1. Right? So note that we understood. I hope you are convinced both mathematically, algebraically, and from the standpoint of circuit theory, that why would we want Y12 to be 0, Y21 to be as high as possible, and Y11 to be 0, and Y22 to be 0, right? This is our wish list. Note that we don't yet know how to make such a network, but if somebody asks us what are you looking for, we can at least tell that person that, hey, can you give us a network which has these properties, because if you can give it to us, we will be able to make a good amplifier, right? So the one last thing before we leave is, if all the wish lists are met, right, what is the incremental amplifier What is the incremental model of an amplifier? So if all wish lists are met, our amplifier should look like this. This is port V1, this is port V2, or Y11 should be 0, Y12 should be 0, so nothing is connected to V1. In V2, I should have one voltage, incremental voltage control voltage source. This is Y21 times V1, and that's it. This is my ideal incremental model of an amplifier. And if I have to stick a input source Vi, and this is what, and if we stick a resistance RL at the output source, at the output node, and this becomes V0, what do you think will be V0 over Vi? V1 is now equal to Vi. This current Y21 times V1 becomes, so this becomes Vi. This current becomes Y21 times Vi. So naturally this voltage becomes minus Y21 times Vi times RL, which means your V0 over Vi becomes minus Y21 times RL. And that is the best that we can do if somebody gives us a network whose incremental equivalent looks like this, right? Okay.